In this video, I want to talk about MOS. And MOS is a great tool to use, especially when you're first learning how to forecast the weather. MOS stands for Model Output Statistics, MOS. And it's a statistical analysis of weather data that compares the accuracy of previous forecasts. Now, MOS uses this concept, and we call it linear regression in statistics. And linear regression is used in MOS in order to make a more accurate forecast. What linear regression is that it attempts to model the relationship between two different variables by fitting a linear equation to some data set. So basically, if you had all these data points, let's say like this is time and maybe this is, I don't know, the y-axis is either temperature or let's say speed, whatever. And then let's say that this was time for an example. These are just arbitrary numbers. But as you can see that all the blue dots, these are all different data points. Well, you can see that there is a very, very obvious trend line. So what we do is we try to fit a trend line to all these data points. And that's exactly what MOS does. And that's pretty much how MOS works. But MOS is just another tool that meteorologists use in order to collect enough evidence to make a forecast. Okay. So this is what an example of MOS is. So there are different types of MOS model runs. So we can either have the GFS MOS or the NAM MOS. And there's a European MOS as well, but because the European model is a little bit hard to find just because it is based off of Europe, if you're an American, you have to pay for the European model. And there's different ways around that. But for right now, for MOS is very, very useful, especially if it's just the GFS and the NAM. And you can get them back to back like this. And this is what MOS looks like. Every MOS model run will look exactly the same. Now the numbers and everything will change, but the format is still basically the same. And looking at this, it's a little bit of a mess. Okay. So I'm going to go through how to read MOS. Okay. So here's an example. This looks a little bit cleaner. So here I've highlighted a couple things. Okay. And here is what each icon stands for. Okay. Now, before I go into all these, I want to talk about what the top looks like. Okay. So this KDEN, this KDEN, okay, this is the station identifier. So this is what is this model forecasting for? What location is this model forecasting for? And in this case, it's for Denver, Colorado, DEN. KDEN is the station identifier for Denver, Colorado. You can see GFS MOS guidance, which means this is the GFS version of MOS. Okay, so this MOS run is based off of the GFS model data. Okay, you can see that the date here, all right, March 4th, 2010, and you can see what model run this is. So this is the 12 UTC model run. Okay, so for us on the East Coast, okay, this would be for 7 or 8 a.m. depending on if it's daylight savings time or not. In Greenwich, this would be noon time, 12 UTC. Remember, everything is based off of Greenwich Mean Time, and you can figure out all the local times based on that information. Okay. Now the DT, the DT is the day of the month. Okay, denoted by the standard 3 or 4 letter abbreviation. Okay, so here you can see March 4th dash. That's when it ends. March 5th, March 6th, March 7th, so on and so forth. Okay. Now it's important to note that 0Z always starts a new day. No matter where you are in the world, 0Z always starts the new day. Why? Because 0Z in Greenwich is midnight, and we know that when midnight comes, it starts a new day, just like it does in local time. Midnight would always start a new day. So 0Z always starts a new day in the weather world, even though 0Z can still technically be the evening time on the day before. So here you can see that we have HR, which stands for the hour in UTC time. Okay. And this is important because this is the hour at which the forecast is valid. Or if the forecast is valid for a period, the end of the forecast period. Okay. So meaning to say, if you look at 0Z, okay, if this was in Boston, let's say this didn't say KDEN, this said, Boston, 0Z, and let's say if this is for March, so it's not daylight savings time, this would be 7 p.m., okay, on March 4th, even though it says March 5th. So this is where Zulu time gets a little bit complicated, especially when we start throwing around dates. This is why I said in the previous video, it's very, very important to understand how to read Zulu time, okay? Now the next line, the N and the X, okay, you can see that there's only a couple numbers on this line, okay? This is the nighttime minimum and daytime maximum surface temperatures. So these are the highs and the lows of the day, okay? So you can see that by 12Z on March 5th, okay, the low, all right, the lowest temperature recorded right before sunrise is predicted to be 27 degrees. Okay, now this is not exactly what happened. This is what's being predicted. As you can see that the model was initialized or ran on the 4th at 12Z. Here's March 5th at 12Z, 27 degrees. Okay, now the high temperature on March 5th, okay, by 0Z, okay, or by 7 p.m., all right, or 7 p.m. for Boston local time. It's 2 hours difference if you're in Denver, Colorado. That high temperature would be 53 degrees. So the GFS MOS model is predicting a low of 27 and a high of 53. Okay, so that's what N/X stands for. It's the nighttime minimum and daytime maximum, okay, for the day. So if you wanted to figure out the highs and lows based off of the MOS model, you would just look at this line, okay, the N/X. The TMP, okay, those are the surface temperatures valid at that hour. So if you wanted to know what the temperature was going to be like at 18Z, it tells you, here's 18Z, 48 degrees. At 21Z, it's 52 degrees. At 0Z, it's 51 degrees, so on and so forth. So MOS always goes in 3-hour blocks, okay? It always will tell you the weather in 3-hour blocks. DPT stands for the surface dew point valid at that hour. So again, if you wanted to know what the dew point was at 18Z, just look below. 25, 25, 27, 29, so on and so forth, okay? Now CLD would be cloud cover, okay? So these are different categories of total sky cover valid at that hour. BK stands for broken. So again, at 18Z, this model is looking for broken clouds. Okay, now what are broken clouds? Well, if you happen to look up at the sky at some point during the day or sometime during your life, and you see that there's a lot of clouds around and then there's a little bit of sunshine, that would pretty much be broken clouds. It's usually about the sky is covered 75% with clouds. Scattered clouds, SC, would be about 50% cloud cover. Okay, so there's some clouds around, but there's still a decent amount of sunshine. We can still say it's a sunny day, but maybe half the sky is covered with clouds or 50% of the sky is covered with clouds. That would be what scattered clouds means. OV stands for overcast. Okay, so overcast would be 100% cloud cover. This would be a totally cloudy day. Okay, and here you can see it kind of just repeats. So this model run is just predicting, some broken clouds, and then some scattered clouds, then it becomes overcast, broken again, and then scattered clouds, so on and so forth. Okay, so this is what that model is basically predicting. What's not listed here is FW, which stands for few, and this would just be a few clouds around, so this would probably be 25% or less of the sky is covered by clouds, and then CL would mean clear, okay, which means there's no cloud in the sky, it's totally clear, okay. WDR stands for wind direction, okay, so it's 10-meter winds or 10 meters above the surface of the earth, and that's the wind direction. So where is the wind coming from, okay? Now these are measured in units of degrees, okay? So here, if you look at this first one, it says 19 at 18Z, and then 14 at 21Z, 13 at 0Z, 16 at 3Z, so on and so forth. Well, if you remember a unit circle from high school, you know that 180 degrees, okay, if you put north, south, east, and west on things, if you put north being 360/0, east would be 90 degrees, south would be 180 degrees, and west would be 270 degrees. If you put directions on a unit circle, this is how we read the wind speed and direction. So 190 degrees, okay, that's very, very close to 180 degrees. So we say that the wind is basically coming from the south. Now here you see 14 and then 13 and then 16 degrees, okay? This basically means that the wind is coming from 140, just pretend that there's a zero after all these numbers. 140 degrees, 113 degrees, 116 degrees. Okay, so we know that 140 is between 90 and 180. So we can say that the wind is coming from what? The southeast. Okay, same thing, southeast. Or you can even say southeast. Okay. The same thing for 20. Okay, so as you can see, 20 is between 270 and 180. So 20 would be from the southwest. 25, okay, 25 is very, very close to 270. So here we see 25, 25, 28, 28, 28, so on and so forth. So we can say that the wind is coming from the west, okay, from March 5th at 12Z through about March 5th at 0Z. So if you wanted to know what the wind direction was going to be like in Denver, Colorado for March 5th, you would say it's primarily about a westerly direction, okay? Which brings us to the next line, WSP. So WSP stands for the 10-meter wind speed given in knots, okay? So if you look, here's 5 knots, 12 knots, 11 knots, 8 knots, 8 knots, so on and so forth. Now in meteorology, what we'll do is we'll usually give a range. Wind speeds are very, very hard to forecast. And for normal operations, for people just walking around in the city, going to work, whatever, wind speeds usually aren't a big deal. So we usually like to give a range. So if you ever watch the Weather Channel and they say 5 to 10 miles per hour or 6 to 12 miles per hour, we usually give a range because wind speeds oftentimes are not constant. Things like P06 and P12, these are the probability of precipitation during a 6-hour period or a 12-hour period. So you can see how there's spaces here, okay? There's not, there's I guess you can say some numbers missing. So here is a 1, a 6, a 14, a 20, okay? This is the probability of precipitation, okay, within a between a 6-hour period. Same thing between a 12-hour period. Okay, so these are all percentages. So this would be 1%, 6%, 14%, 20%, so on and so forth. And if you want to know how much, well, what's the chance that it's going to rain or we're going to get some kind of precipitation in a 12-hour period? Well, it's 15% or 27%. So it doesn't really seem too confident that it's going to rain. It might just be a little cloudy based off of this MOS data that you've seen so far. So that's exactly how you read MOS. So when you actually go to click on MOS, right, and if you use MOS to figure out your forecast, now you understand what all these different lines mean.